Hello everyone. In this video we are going to talk about making rough schematic sketches of rational functions. I'm assuming you're already familiar with how to do rough schematic sketches of polynomial functions, and this is going to add a few more details like vertical asymptotes and horizontal asymptotes. So, first of all, let's remember that a rational function is a function of the form f of x equals p of x over q of x, where both p of x and q of x are polynomial functions. It's called a rational function because it's a ratio of functions, but in particular it's supposed to be a ratio of polynomial functions. One important fact about rational functions compared to polynomial functions is that they have a domain that is not all the real numbers. And the difference is that, well, because it's a ratio, you're not allowed to divide by 0. And so the zeros of the denominator polynomial are values that are outside the domain. And so the domain is the set of all x such that q of x is not equal to 0. In words again, the set of all x such that q of x is not 0. So, for this video, we're going to assume that p and q have no common factors, or in other words, they have no common roots. That's actually what we care about. And the reason for this is, well, let's see through an example. So let's have f of x be the function x minus 1 times x minus 2 on the top and x minus 2 on the bottom. So we can see that there is a common factor of x minus 2. Or in other words, they both have 2 as a root. Because there is x minus 2 in the denominator, that means that the domain is the set of all x where x minus 2 is not 0. Or I could write that as the set of all x where x is not equal to 2. Or I could put that into interval notation. It's all the numbers from minus infinity to 2, exclusive, and then union with 2 exclusive all the way to infinity. On the number line, we can write it as such. Use a circle where the number is not included, and then a bold line everywhere else. So that is the domain of this function. So at x equals 2, this function is not defined. That's what the domain means. But for x away from 2, then the function is defined, and we can actually cancel out the common factor to get x minus 1. That's just a line. So if we were to graph it, then we would draw this line y equals x minus 1, and then draw a circle right at 2, or when x equals 2, and that represents the fact that that point is not part of the graph of f of x. And this sort of missing value is known as a removable discontinuity. So the reason that we are going to exclude the case of common factors is that all they can do is create removable singularities. So in other words, you can cancel everything out, and then every factor that was canceled out, all you have to do is then draw a circle at each point corresponding to each canceled out root. So that's the method for assuming you know how to draw the graphs when there are no common factors. Okay, so some background knowledge is that there are some graphs that we should all know. So let's start with y equals 1 over x. So 1 over x has a vertical asymptote at 0. That's where the function is not defined. And as x gets, so when x is positive and small, so say, 0.001, then 1 over 0.001 would be 100, which is big and positive. But if x is negative 0.001, it's going to be negative 100, big and negative. When x gets larger and larger, both in the positive and the negative direction, the function gets closer and closer to the x-axis. So there's a horizontal asymptote. That is the x-axis. 1 over x squared, the difference here is that for negative numbers, it's being squared, so it's positive. The picture on the positive side of the y-axis looks fairly similar, maybe a little steeper when you get closer to the y-axis, but on the negative side, the graph is flipped over. Y equals 1 over x cubed. It looks like 1 over x, but steeper still. Because remember, when you take a negative number and cube it, it's still negative. And so that's why it looks like 1 over x, except we're cubing it, so the numbers get bigger still. And 1 over x to the 4, it looks a lot like 1 over x squared. In general, the way you can quickly draw a quick sketch of these graphs is that if you have 1 over x to the k, where k is odd, it looks like 1 over x. And when k is even, it looks like 1 over x squared. So those are graphs that you should know. So whenever you have, so once we know these graphs, we can also know what the 1 over x minus r to the k graphs look like, and that is using graph transformations. The x minus r is representing shifting the 1 over x to the k graph r units to the right. So let's look at what that would look like for 1 over x minus 2 cubed. And so we are taking the 1 over x cubed graph and shifting it 2 units to the right. And that puts a vertical asymptote right at 2. And this makes sense because when you plug 2 into this graph, it is undefined because we get 2 minus 2 in the denominator, which is 0. So that's where the asymptote ought to go. And also we can check that if x is slightly bigger than 2, then we get a positive number. And when x is slightly less than 2, we do get a negative number. So that is the graph of this shifted 1 over x cubed. So now that we've gone over some of those basic graphs that we should know, here are, just like in the previous video about rough sketches of polynomial functions, here are 3 big ideas for how to roughly sketch a rational function. F of x equals p of x over q of x, where we assume there are no common roots because that simplifies the explanation. So big idea number 1, before for polynomials it was that polynomial functions are continuous. The difference now is that it's not continuous because the function is not defined at whenever q is 0. However, there are vertical asymptotes at the zeros of the denominator. These are known as poles, and f of x is continuous away from these vertical asymptotes. Big idea number 2 is that for large x, the function can be approximated by taking the leading term of p of x divided by the leading term of q of x. This is like for just polynomials where you can approximate them for large x by just the leading term, but we have a quotient of polynomials, so we can take the quotient of the approximations. So let's look at an example for that. So f of x is 2x cubed minus blah, blah, blah over x plus 1. So when x is large, then the leading term is 2x cubed for the numerator and x for the denominator, and that gives us an approximation, which simplifies to 2x squared. So if we zoom way out, we know that our graph is going to look like a parabola, but when x is very near the origin, or when x is near the origin, then that's where the interesting stuff is going to happen. So let's look at another example. This is 2x squared minus 2 over x squared plus 4x plus 4. And in this case, when x is large, we have 2x squared over x squared, and the x squareds cancel out, and we're left with 2. So in this case, the degrees are the same, and the approximation, when we zoom way out, it's going to look like a horizontal line with the interesting stuff happening somewhere in there, in the middle. And lastly, let's look at a third case. So the sequence of these cases is the numerator has a larger degree then they have equal degrees, and now the denominator has a larger degree. So if we zoom way out, we want this approximation, and we see that it's x over 2x cubed, which is 1 over 2x squared, which looks like so. It's the 1 over x squared graph, but divided by 2, which I'm not, we have no scales here, so we're not really caring about the 2 itself. We only care if it's positive or negative, because negatives flip the graph over. Okay, so we're going to use this zoomed way out approach to figure out what the graph looks like away from all the zeros and the poles, and then we can use that to fill the rest in once we figure out some details of the zeros and the poles. Which leads to big idea number 3, information about the zeros and the poles. So just like for polynomials, where when x is near a root of the polynomial, it looks like just x minus r to the k. So here, same thing. When it's a root of the numerator, then the graph looks like x minus r to the k, where k is the multiplicity of the root. And this plus or minus is representing that we don't know if it's going to be going upwards or downwards. It might either look like this or it might look like that if it's odd, or it might look like this, or it might look like that if it's even, just like for polynomials. So when x is near a root r of q of x, remember these are the poles, instead of x minus r to the k, it's 1 over x minus r to the k, where k is the multiplicity of the root of that denominator. And that's why we want to know what the graphs of 1 over x to the k look like, so that we know what the graph looks like in general. So why is this the case? So I'm going to abbreviate the details here. It's just like in the previous video, where we can approximate f of x near a root of p of x or a pole by plugging r into all of the factors except for the x minus r factor, and that gives us a good enough approximation near r. And then from there we see that it's one of these two cases with some coefficient out front, which could be anything that's any non-zero coefficient. So what we're going to now do is go through the 3 examples that we looked at when we were in big idea number 2, and we're going to go through this process and come up with a rough sketch of each of them. So let's start with the first one. What you want to do first is take it and factorize it using any method you have, if factorization is possible. And then once it's factorized, you want to figure out the zeros and the poles. So the zeros come from the numerator and the poles come from the denominator. So for the numerator, we've got x plus 2, which contributes a minus 2 root with a multiplicity of 1. And the x minus 1 contributes a 0 of 1 with a multiplicity of 2, because that is the exponent. And then we've got x plus 1 in the denominator. Those give the poles. There's just one pole from the 1 root, which is minus 1, and has multiplicity of 1, because this is just this one factor. And as before, we figured out the zoomed out picture, which was 2x squared, so it should look sort of like a parabola. And so that's the picture that we should expect. Let's reproduce this picture from scratch. So the way this works is that you take the, so let's see, we've got minus 2, 1, and minus 1. So we're going to want some space for each of these. Minus 2, 1, and minus 2, minus 1, and 1. We've got a 0 at minus 2. We've got a 0 at 1. We've got a pole at minus 1, so a vertical asymptote. We know the zoomed out picture, which is that it looks like x squared, so we know it's going to go out like this. And then we know from here that it has to hit the root at minus 2. And the multiplicity there is 1. So that means that when it hits the root, it has to pass through like a line because it's a multiplicity 1 root. Then from here, because it's continuous, it can't cross this axis, the x-axis, and instead it has to come up to the asymptote and do a vertical asymptote that way. Now, what kind of asymptote is this? It is a multiplicity 1 pole. So that means that it's going to have to look like 1 over x or negative 1 over x. So it comes from the other side. And then we know we can't cross the x-axis until we hit this root. And that root at 1 has multiplicity 2, so it's going to look like a little parabola. And then there we go. Let's connect it up using continuity. So that's how I came up with this picture on the left-hand side. Let's look at what it really looks like. So here's a picture plotted. And the thing about these schematic sketches is that what they allow you to understand is details of the graph that you wouldn't be able to see if you're not necessarily guessing the correct ranges to view the graph from. So, for example, I found out that just by kind of knowing what the graph looked like and zooming out enough, I could see at least all the roots by going from -3 to 3 and -40 to 40 to see both the roots at -2 and 1, and also to see enough information to get that there's a vertical asymptote at 1. Furthermore, by zooming much farther out, we can see that it actually does look like a parabola when we zoom out really far. So anyway, the schematic picture lets us be able to predict that that is what we would see. And we know that we've seen all the main details. Okay, so now let's look at the second of the 3 examples. And that was 2x squared minus 2 over x squared plus 4x plus 4. So first step, factorize if you can. So we can pull the 2 out and then get x plus 1 and x minus 2 on the top. And on the bottom, get x plus 2 squared. So the roots of the numerator give us the zeros, and the roots of the denominator give us the poles. So we have -1 from the first factor, 1 from the second factor. Those are the zeros, and they each have multiplicity 1. And the denominator is -2 is the pole with multiplicity 2. And as we calculated earlier, the zoomed out picture should look like a horizontal line. In particular, it's a horizontal asymptote. Okay, so we have that. And let's reproduce this picture from scratch. We have interesting things happening at -1, 1, and -2. So let's make sure we have enough space for that. I'll put my vertical axis here. And I've got 1, -1, -2. I've got zeros at -1 and 1. I've got a vertical asymptote at -2. I have a horizontal asymptote at 2. And I know it's a horizontal asymptote because that's what happens when you get a constant. And also, when we zoom really far out, it looks like a line. So that means that it must come up to that line and converge to it. So what else do we have? We know that, so this is where we have to figure out so does it come down to the asymptote or does it come up to the asymptote? If it went down to the asymptote, then there'd be no way for it to, well, I guess we don't actually know using the information that we have. We would need some calculus. Well, in any case, we know that it can't be this way. It can't go down through the 0, because if it did, how would it come back up to the asymptote? So we do know that at least it has to go this way. It has to go up through the 0 at 1. And then it goes up to the asymptote that way. Then we have at -1, there is a root of multiplicity 1. So it's going to go through like a line. And to meet the continuity condition, it's going to have to be a downward sloped line. And then we can connect up like so. Then there's a vertical asymptote at -2 with multiplicity 2, which means that it's going to either look like this or it's going to look like that. The latter can't happen because it would need to connect up and there are no zeros in between. So it must be going up to this asymptote and it's multiplicity 2. And then secondly, it's going to go off to the horizontal asymptote at 2. So that's how that picture came about, puzzling all this together. Let's look at the real thing. So I plotted this, and it took some thinking about the, experimentation with what the axes bounds should be. And with that, well, first of all, we can at least see the vertical asymptote that's somewhere between, or somewhere around -2 maybe. And then also there's a root at -1 and or a 0 at -1, a 0 at 1. And it does go above and below the axis as we see here. But from this picture, we can't really see the horizontal asymptote very well. So if we zoom way out horizontally, we can see that at 2 there does seem to be a horizontal asymptote. Okay, let's look at the third example. The third example was the reciprocal of the first example. So factorization, we've already done it, but now it's just upside down. And we've already figured out all the poles and zeros, but they were called zeros and poles in the first example. Okay, so we've got our zeros and poles. And zoomed out, let's take the leading terms. We've got x and 2x cubed, and that gives us 1 over 2x squared as our approximation when we zoom way out. And 1 over x squared is roughly that. And so now with all that, we can put together a picture. Let's do this live. So we've got -1, -2, and 1 as interesting things that happen. So those are some places. There's a 0 at -1, and that's the only 0. There's a vertical asymptote at -2 from the pole, and a vertical asymptote at 1 from the pole, the other pole. And so we know that the long-term behavior is that it goes toward the x-axis when x gets very large. So then we're going to hit this asymptote, and we can't cross the x-axis, so this one has to go up. And what's the asymptote at -2? Multiplicity 1. That's odd, so it has to flip over to the other side. And then it comes up to the 0. What's the multiplicity of that 0? It's 1, so we have to go through it like a line. And then we can't go back through the x-axis because there are no other zeros. And then we can come up to this asymptote and go up. And what kind of asymptote is it? This pole has multiplicity 2, so it has to be the same side. It's both positive or both negative. So 1 was positive, so they're both positive. And there's the picture. So let's look at what that looks like. So we can see, indeed, there is a pole at -2, and it's an odd one. And there's a pole at 1, and it's an even one. And there is a 0 at -1. Okay, so that was that third example. To finish things off, let's do one more example with a lot more things going on. So let's do a rough sketch of this rational function, all factored out with no common factors. Let's look at the numerator. There is a 0 at 1, 3, and 4 with multiplicities 2, 1, and 1. So that's this first table. And the denominator shows poles of 2 and 5 with multiplicities 2 and 3. What does the zoomed out approximation look like? f of x is, so how do you get the leading term from a factorization? What you can do is you can just delete all the constants. So we've got minus 2 times x squared times x times x. So that's minus 2x to the 4. And the denominator is x squared times x cubed, which is x to the 5. And that simplifies to minus 2 over x. So our approximation, when zoomed out, should look like 1 over x, but flipped over and stretched by a factor of 2. So let's put this all together. All of our interesting features are at 1, 2, 3, 4, and 5. So let's make sure that we have tick marks for each of those. So 1, 2, 3, 4, 5. I'm going to label them so that I don't get lost. So we've got zeros at 1, 3, and 4. And we've got poles at 2, so vertical asymptote, and a vertical asymptote at 5. And we know that when we zoom way out, it's going to be above the x-axis on this side and below the x-axis on this side. Okay, so let's start on the left side. So what is the multiplicity of the 0 at 1? It is multiplicity 2, and we're coming at it from the positive side, so it's going to come down and look like a parabola. Then there is a asymptote at 2, so we're going to go up and do the vertical asymptote. And what is the multiplicity? The multiplicity is 2. That's even, so it's going to come back on the other side as well. With this, it's going to be positive, just like the left-hand side. 3 has multiplicity 1, so that means that when we come down to the 0, we're going to go straight through it like a line. 4 has a multiplicity 1, 0, so when we come up to it, we'll go straight through like a line. And then we come up to the asymptote, go up vertically. That pole has multiplicity 3, so that's odd. So we're positive on the left side, that means we'll be negative on the right side, which matches up exactly with where we need it to be. So that's how this picture came about. And let's look at some plots. So we can see in this plot that at 1, 3, and 4, there are zeros. And at 2, it looks like that there's a vertical asymptote. But over past 4, it's really unclear what's going on. And without the schematics that we have produced, we wouldn't have any idea that there'd be anything that we should be looking for. So zooming much farther out, in the y-axis direction, we can see that indeed there is a branch of this graph that is popping into existence over here. But the issue with zooming so far out is that you start losing details of all the things that are very close to the x-axis. And just one last graph, zooming very far out in the x-axis direction, we can see that it sort of looks like 1 over x, or minus 1 over x, which is the approximation that we had for this function. Okay, so that was an introduction to how to create some rough sketches of rational functions by taking factorizations of the numerator and denominator and using the numerator to find the zeros and the denominator to find the poles, and then filling everything in using the multiplicities and some other observations. And so with that, you know about how to plot a good number of interesting functions. So see you next time. Goodbye.